Hey, my name is Dan Rosen. I'm an instructor here at Maracana, and I teach Scala courses. And I'm here in Maracana's new studios to talk to you about type classes in the Scala language. Now, type classes are a design pattern that we try to use as much as we can, and we use them really just with one goal in mind, but it's a very important goal in software engineering, which is decoupling. We want to try to keep our software as modular and as decoupled as possible so that we can vary our little bits of our program independently, so that we can swap things out, we can reuse them, and so on. And so that keeps things much more maintainable and easier to reason about over time. All right, so let's jump into it. Let's get started here with a simple use case. I'm going to define an algebraic data type that's going to be used here to represent mathematical expressions. What's an algebraic data type? Well, it's sort of another pattern in Scala that you see where we have a sealed trait. In this case, it's my sealed trait called expression, and then a number of case classes that implement my ADT trait. So in this case, we've got case classes number plus and minus. And the fact that we're calling it an algebraic data type is actually has nothing to do with the fact that we're talking about mathematical expressions here. That's sort of an unintended pun. Okay, so a number has, of course, a value, and if we wanted to actually evaluate the number, all we would have to do is get its value. Plus and minus are sort of our recursive cases in this little expression language. They have sub-expressions on their left-hand side and right-hand side, and so of course to evaluate a plus and a minus, we would have to evaluate the sub-expressions first. Now that's what our expression evaluator down here is doing. It pulls the value out of a number, and for pluses and minuses, it recursively calls value on the left-hand side and the right-hand side arguments, and then adds them or subtracts them appropriately. One thing that I want to point out, and this is an important thing to start with, is that I could just as easily have defined value as an abstract member on the expression trait, rather than having it separated out into this expression evaluator thing. So that would look like, sealed trait expression with a member def value that would be just abstract, and then my case classes number plus and minus would have some implementation for value. And those implementations would look just the same, but, let's say that I don't want to necessarily bake in the assumption that I'm going to be evaluating expressions. Let's, start out instead with the assumption that expressions could be used for any number of different things. So you might want to evaluate them, or let's say you might want to serialize expressions so that somebody else could evaluate them elsewhere. Before we look at what other things you might want to do with expressions, let's just take a quick look at the coupling here that's implied by our class diagram. We have our expression evaluator, which depends upon expressions, and that's sort of what you would expect. That's probably what we're going to think of as necessary, because what's an expression evaluator to do if it doesn't know what it's evaluating, right? And, of course, we have some sort of an inheritance dependency from number plus and minus to the sealed trait that they implement. So again, we think, well, that's probably relatively necessary. And so, the fact that we have decoupling as our main goal doesn't necessarily mean that this coupling in particular is bad. It wanted to get everybody's mind on how we'll quantify coupling, and so this is how we're going to be representing it. Okay, so we talked about other things that we might want to do with our expression hierarchy, and indeed, let's say we wanted to serialize it. So let's say I want to serialize expressions into JSON, the JavaScript object notation. So once again, I've defined a new algebraic data type, this time for JSON. And this basically just mirrors the spec. So I've got a JSON value ADT with case classes JSON object, array, string, number, boolean, and null, which nothing ought to be too surprising there. An object is just essentially a dictionary from field names to their values. An array is a sequence of values, and then the rest are basically our primitives. Again, we have sort of a little class diagram here that indicates what kind of coupling is implied by this structure. JSON writer we haven't looked at yet. We're going to look at that on the next slide, but the goal, of course, is going to be to serialize JSON values out of whatever type into a string so that we can send it over the wire. So, of course, we think that a JSON writer has sort of a necessary dependency upon JSON values, and then of course the case classes that implement it, by virtue of extension, those are also going to have dependencies on the JSON value trait. again, not passing judgment here, just observing what the degree of coupling that we've got is so far. Okay, just a quick look at the writer. I've included this in here just sort of for completeness. So if you're following along and you want to implement these things for yourself, you can do it. The implementation detail, not that important, but again, we've separated out the concern of serialization of these JSON values from the ADT itself. Again, I could have implemented a write method in the ADT, but I feel like it's a cleaner approach to externalize it and then use pattern matching on the case classes. Okay, so we said that we wanted to be able to serialize expressions in our little expression ADT out to JSON values. So what we want to do is utilize what we've got so far. We want some way essentially to reduce that problem into converting expressions to JSON values. Because once we do that, then we can use the write method that we've already defined. So down at the bottom here, I've got this sort of auxiliary write method that's going to take a value of some arbitrary type that I haven't really defined yet and return a string. And the way that it's going to do that is by doing some sort of a conversion to JSON values and then just chain back up to our default write method. The typical way that you would do this in an object-oriented design is by introducing some sort of an interface or a base trait, and things that you'd want to be convertible to JSON values should implement that trait. So this is how this would typically look. I would introduce some sort of a trait called JsonConvertible, let's say. Value is going to have to be a JSON convertible type, and then when we want to actually serialize this thing, all we have to do is call convert to JSON on the value. So that's what that trait would look like. Just a single method trait, JsonConvertible, with that one method, convert to JSON. Again, a look here at sort of the dependencies. JSON writer now has two dependencies instead of just one. It has a dependency on JSON value and a new dependency on JSON convertible. I think that looks fine so far. So now the interesting part is when we have expression trying to sort of fit into this model. So we say expression extends JSON convertible, and what that means is that we have to implement a def convert to JSON inside each of our case classes, number, plus, and minus. Again, the implementation isn't that important here, but if you want to pause the video and copy down to follow along, please feel free. So, this approach that we have totally works. We can declare an expression, plus with its left-hand side is just the number 1, and the right-hand side is a sub-expression minus, where its left-hand side is the number 3, and the right-hand side is the number 2. And when I go to serialize that using JSONWriter.write, it's perfectly happy to do so because expression is a JSON convertible. But really, I don't like this approach. I think there's too strong coupling here, because as soon as we said that expression inherited from JSON convertible, we introduced quite a bit of unnecessary dependencies. So, for example, here you can look at this class diagram and see that, well, expression evaluator depends on expression, which transitively depends on the thing that it implements, which sort of implies that expression evaluator cares about JSON convertibility, which, of course it doesn't. That's an orthogonal concern. Also that this really goes against the design pattern that we've been trying to follow so far, where our ADTs were simply data and no methods attached to that data, in keeping the assumptions about what the data might be used for external. And so that was kind of a design goal that we've failed to maintain here. But furthermore, what if expression were some sort of a third-party library, something that we can't edit, we can't commit to, and therefore we couldn't modify expression to inherit from JSON convertible if we want to be able to serialize these things to JSON. So the approach just completely fails here. This approach of subtyping, subtype polymorphism, which again is just expression being a subtype of JSON convertible, it's not going to work for us. So we're going to introduce this notion of type classes, or ad hoc polymorphism as compared to subtype polymorphism, to try to eliminate that tight coupling. Now, ad hoc polymorphism or type classes are maybe sort of fancy sounding computer science-y terms, but it's really quite straightforward. Whereas we had a trait before that was going to be convertible to JSON, we're going to externalize this JSON convertibility property into a helper object. So now our auxiliary write method is taking two arguments. It's taking a value of some type A, and this is an arbitrary type that's just noted in the type parameter, and a converter for type A. So we've got two arguments here, and this is doing essentially the same thing as we had with subtype polymorphism. It's just sort of splitting it out. So now instead of saying value.convert to JSON, we say conv.convert to JSON with the value. And we can then pass that to our default write method again. So again, what does this look like? Well, we've got now our JSON converter for type A, so it's now a parameterized trait. And convert to JSON now takes an argument, some value of type A. Our dependencies, again, look fairly similar. JSON writer has a dependency on JSON value and on this JSON converter trait. And I've colored this JSON converter trait in green to indicate that it's somehow different. And what I really want this to highlight is that JSON converter is now what we're going to think of as a type class. It's something that I can implement for anything that I want to be convertible to JSON without having to, make that thing extend from some base type. So JSON Converter is going to be our type class here. So the benefit that we get from this is that expressions now get to be just what they were before. They get to be raw data with no methods polluting them. So we've got the original expression ADT, and we've separated out the logic of how to convert our expression ADT into our JSON value ADT. This is great. Now we can call JSONWriter.write with our expression again, and as long as we pass in the expression JSON converter that we just defined, we still get the value at the other end that we wanted to. But looking at the class diagram here, you can see also that the fact that we've separated things in this way eliminates that coupling between expression and JSON, what we had previously called JsonConvertible. Now the dependency is encapsulated just in this one value, this expression JSON converter, that's of type JSON converter for expressions. So, again, what we had observed before is that the expression evaluator, which depended upon expression, seemed to have this transitive dependency upon JSON conversion or JSON convertible. And that is no longer the case. It's quite nice. Now we have, really just a minor problem at this point, and that minor problem is essentially that it's slightly more verbose. The fact that we have to explicitly pass this expression JSON converter in is a little bit more clumsy than what we had before with our subtype polymorphic approach. And we can also sort of consider it a minor fail that nothing that we've done so far is really special to Scala. We can take this design pattern that we've implemented so far straight out of the Gang of 4 Design Patterns book and implement it in Java or in C++ or whatever. And so Scala doesn't offer us any special advantage so far. So here's where we're going to see Scala's expressive power using implicits. So just a quick review for anybody who needs a quick brush up on how implicits work in Scala. I'm going to go into my Scala interpreter here and just define a quick add method. It's going to take two arguments, x and a y, and add them. So nothing too special. I can also curry those parameters into multiple parameter lists. And this looks a little bit unusual if you're more familiar with Java or C++ or some language like that. I've got two separate parameter lists, each of which just contain one member, x and y separated out. And if I want to call add, I can do so. I just have to make sure to pass my parameters in separate parameter lists there as well. Now the next thing I can do is say that the last parameter list, I can have an arbitrary number of parameter lists, right? But the last one, I can optionally include this implicit keyword. And what that says to the compiler is if it's able to find a value, in this case a value of type int, in implicit scope, that the compiler should provide that as the argument to that parameter list. Now I can call add here just as I had done above. I can explicitly pass in 1 and 1, and it'll still give me the result that I expect. But let's say that I want to actually use this implicit power to try to just add 1 and pull my second int value out of the ether. So let's try to do that. I'll try to just say add 1, and it says, oh no, I couldn't find an implicit value for parameter y. Well, that's because I don't actually have one. There is not an implicit int in scope. So let's introduce one. We can say implicit val1 of type int is equal to 1. And now I can just call add 1, and the compiler, or in this case the REPL, will provide that implicit value as the implicit parameter for that second parameter list. Okay, so that was just a quick review. But basically, armed with this power of implicits, we can now take this converter parameter that we had explicitly and separate it into a separate implicit parameter list. All that we need to do now to satisfy the requirements of implicit resolution is say that our expression JsonConverter that we had defined previously is going to be an implicit val. I haven't made any changes to this thing otherwise. And then finally, we get really essentially the complete win here. We can say JsonWriter.write, just pass it the expression. We no longer have to explicitly pass the type class instance that we had defined, this expression JsonConverter thing. And so this syntactically looks exactly like what we had when we were using subtype polymorphism. But of course, we have removed all of the JsonConverter stuff that was polluting the expression ADT. So this is really great. And if you followed so far, that is really essentially type classes in Scala. You don't need to learn anything more to use the type class pattern in Scala. So if you feel like that's enough to absorb, then feel free to stop the video right now. What I'm going to show you from this point on is sort of a bonus. It's going to be a syntax that'll help us deal with type classes as even more of a sort of a first-class language construct. So above we have just what we had before. We've got our two parameter lists, one taking our value that we want to convert to JSON, and the second implicit parameter list taking our type class instance. But we can express that in sort of, like I say, a more first-class way in the language using this context-bound syntax, where we say that A is context-bounded, and that's what this colon means, by the JsonConverter type class. Or, another way of expressing that is A is a member of the JsonConverter type class. And this should sort of remind you of how you would put upper or lower type bounds on a type parameter to a method or to a class that you're defining. It's supposed to be sort of reminiscent to that syntax. And so that's quite nice. The only downside here is that we no longer have this variable named conv, so we have to create one. I've done that by calling the implicitly method. This is something that Scala's predef provides for you, and that basically pulls our JSON converter out of the implicit scope and assigns it to a value conv. So, that has an advantage and a disadvantage. The advantage is we get to use this context-bound syntax to say A is a JSON converter. So that's kind of nice. It provides a sort of a documentation of what A has to be to satisfy the constraints of this method. But the downside, of course, is that I've got to use this implicitly method in the body. So I want to try to clean that up a little bit. And the way that I'm going to do it is a really straightforward refactoring. We're just going to rename JSON converter. We're going to call it JSON. Because we're thinking now of the JSON type class. We're not thinking about conversions. We're not thinking about sort of the verb. We're thinking just about the noun JSON as a type class in its own right. We're going to say that the type class has a method called JSON. And then the way that we're going to use that in our JSON writer is we'll say, A, again, is a member of the JSON type class. That's using our context-bound syntax. And now we can say a little bit more fluently that when we want to call write, we'll use the implicit JSON type class. And we'll just call .json on that. Now, thinking about it this way actually gets us back to a class diagram that looks similar to what we had before using subtype polymorphism, using our inheritance, right? We have JSON writer, JSON value, and JSON, all sort of interdependent. And we have expression evaluator dependent on expression. And those are sort of as we expected. And now we have this thing using context-bound syntax that makes expression look like it sort of is inheriting in some way from the JSON type class. Now, of course, we know that it isn't in reality. It's using this implicit plumbing. And so expression doesn't actually have any dependency upon JSON. But we can write, this dotted arrow here to sort of indicate that expression is a member of the JSON type class. And that'll help us think about things a bit more succinctly. All right, so now that we've got this kind of mental model for how we're dealing with type classes, let's see what else we can apply this pattern to. Let's say, we started out with the assumption that expressions were going to be a closed ADT. That is, we had a sealed trait expression, and we had number and plus and minus that inherited or implemented expressions. But let's say that we want now to open that up and be able to treat anything as an expression in some way. The same way that we had JSON as sort of an open type class, such that anything could be treated as a JSON value. And just for the sake of example here, let's say we want to use Scala's built-in int and tuple2 or pair types to be able to treat those both as convertible to JSON and treatable as or evaluatable as integer expressions. So we're going to use the same type class pattern for expressions as we use for JSON. So I'm going to define an expression trait, and that's going to be my expression type class. So again, you notice the expression now takes a type parameter, some type A, and our value method is taking an expression, again, of that type A, and yields an int. The expression evaluator that we had before now gets very much simplified. We now just have an evaluate method that takes an A of the type class expression. You give it an expression of type A, and it uses the implicit expression type class instance to determine the expression's value. So we no longer have to do any sort of pattern matching on the concrete subtypes of our expression ADT, though those no longer exist now. And just to take another look at what our class diagram is going to represent in terms of coupling, we've got our JSON writer family off to the left, and we've got our expression evaluator family off to the right. But those are no longer tied at all to the concrete implementations of the things that we're going to be converting to JSON, or the things that we're going to be evaluating as an expression. So int and tuple2 are both members of these type classes now, but again, I've represented these with dotted arrows to indicate that there's no actual dependency there. Okay, so let's look at how we declare type class instances for these two type classes for int and tuple2. So let's start out with JSON. In the companion object, just sort of for convenience sake, in the companion object for our JSON type class, I'm going to declare these two implicits. One is going to be the type class instance, sort of the assertion, if you will, that int is a member of the JSON type class, and the assertion that pair is a member of the JSON type class. These are our type class instances. So for int, obviously, I'm just going to give back a JSON number anytime you ask for the JSON value of an int. And for pairs, I'm going to perhaps somewhat arbitrarily say that that JSON object is how we're going to represent these pairs. So it's going to be a JSON object with a map with the fields first and second. And now we do something interesting. We've made the assertion that pair is a member of the JSON type class, but we've put the constraint on it that a pair of type T1 and T2 is only a member of the JSON type class if T1 and T2 themselves are members of the JSON type class. So given that assertion, now we can call our implicitly method again to pull the JSON type class instances for T1 and T2 out of our implicit scope. We'll call .json on those, and thus we can convert the first and second elements of our pair to JSON recursively. Another thing to sort of point out here is that this is open to extension. So if somebody else provides some other JSON type class instances that are available in implicit scope, then at the point where I am doing my JSON writer.write, as long as those are all in scope, I can call int JSON, I can call bare JSON, and I can call whatever other JSON things are provided implicitly. The compiler, again, will take care of all of that type class membership through implicit resolution. Now we get this nice symmetry with JSON instances and expression instances. Again, in our companion object for the expression type class, I've gone ahead and defined two implicits, which again are asserting that int is a member of the expression type class, and pair is a member of the expression type class, with the assumption that, of course, pairs constituent bits, t1 and t2, themselves also have to be viewable as expressions. So to evaluate an int, well, the value is just the value of the number, right? And to evaluate a pair, again, sort of arbitrarily, I'll say that a pair represents addition. So I will implicitly get the value for t1 and the value for t2 out of our implicit scope, again, using whatever implicits are available in implicit scope at the time. So we're not just limited to our ints and our pairs. We're open to extension again. And so I'll get those values and I'll add them, and that'll be the value for our pair plus expression. So this is great. Given that those things are in scope, again, by virtue of the fact that that our companion objects are declaring them, I can say, val foo is equal to this tuple of 1 and an inner tuple 2 and 3, and I can call JSONWriter.write on that. And I can call expression evaluator.evaluate on that. And in fact, since we're using implicit resolution, we can not only provide additional things to be treated as JSONs and to be treated as expressions, I can also override things that I've defined before. So let's say, for example, that instead of treating pairs as addition, when I view them as expressions, I want to treat them instead as subtraction. So I've overridden, essentially, by virtue of how implicit scope resolution and the precedence there works out, I've basically redefined pairs to be treated as minus. So if I call expression evaluator.evaluate on foo now, using the same foo, I haven't done anything different, I'll get 2 out the other end instead of 6. So this is great. To summarize, a type class is this thing that we've seen, basically a trait with a single type parameter. For example, JSON of A, and that defines operations on its member types. More advanced, actually, you can get into multi-parameter type classes where I could have, some type class with a and a b parameter or so on. That's a bit more advanced. And then for a type T to be a member of this, some type class TC, there just has to be a value of type TC of T available in the implicit scope. And again, that's really the essence of what the type class pattern is all about in Scala. If we want to get a little bit more, sort of syntactic sugary and treat these type classes as kind of a first class member of the Scala language, we can use context-bound syntax, saying T colon TC to indicate that T is a member of this type class. And again, that's supposed to look similar to lower or upper type bounds, right? So finally, just to summarize, the thing that we had used initially was something called subtype polymorphism, which you actually have to use sometimes. You can't actually always use ad hoc polymorphism. There's some cases in which you can't get away with that. But the disadvantage to using subtype polymorphism when you need to is that you get this sort of tight coupling, where the subtype, by virtue of its inheritance, is tightly coupled to the supertype. Now, in the cases where you can get away with ad hoc polymorphism, it's generally a very good idea, because when you use type classes, there's no coupling whatsoever between the type classes and their members. I can mix and match instances of the type class, these vals that are in implicit scope, or these defs that are in implicit scope. I can mix and match those as I want to. So that really opens up the door for quite powerful decoupling and modularity. I can do things like dependency injection using this technique, and that's going to help out a lot with testing in large code bases. I can reuse components that were designed for some problem domain A in some new problem domain B, if I can provide appropriate instances of the type class for this problem domain B. So this is really a powerful tool for software engineers, and one of the big appeals of Scala and other related functional languages. Thanks again for watching. I hope you guys understand now how to use the type class pattern in Scala to really keep your code nicely modular and decoupled. And if you'd like to learn more about Scala, please visit our website.